Hello and welcome to Calculus 1, Lesson 1C.1, Limits to Infinity. I want to start us off with an example. We're going to consider f of x being 3 over x minus 2. Now take a moment and see if you can visualize what the graph of this function is going to look like. This is a rational function. It has only one linear factor on the bottom, and it zeroes out at positive 2. So we should expect to see a vertical asymptote at positive 2, right? Let's take a look at the graph. Right, so here's our function, and then our vertical asymptote is right there at 2. Now there's two other things we can say about what's going on there. We can say that it is discontinuous at x equals 2. Or that it is undefined. We cannot plug 2 into this function because it would be undefined there. But what if we want to try to get close to 2? What can we say about the behavior of this function as x is getting close to 2? Well, if we look at what's happening from the right, okay, when x is approaching 2 from the right, what we see is the y value is going to increase without bound. This is running off to infinity and beyond, right? This blows up. It gets crazy big as x approaches 2 from the right. So in this kind of way, I want to say that limit's equal to infinity. Okay, and what about from the left? As x approaches 2 from the left, it falls down towards negative infinity. It blows up in the negative direction. So in that way, I want to say that this limit is equal to negative infinity. Now just like with regular finite limits, when they don't match, we want to say that the limit doesn't exist. So we still have that limit does not exist. Let's look at another example. Let's let g of x be 1 over x plus 3 squared. Here's our graph. Right? A little bit different behavior than what we had before. What are the one side and two side, or the left side and right side limit of these? And this is definitely supposed to be a negative 3 there. Make that pink. Negative. And negative. Okay? Well, in either case, it's blowing up off to positive infinity, right? Whether we approach from the right or from the left, these are running off to infinity. So, positive infinity, positive infinity. Now these two things agree. Unlike the last example, they agree. And so we can talk about the two-side limit as x goes to negative 3. Thank you. We can say that that limit is infinity. The two-side limit is infinity. And we'll see this type of behavior in all kinds of rational functions. If you've got a root of a rational function, a root of the denominator of a rational function, one thing that could happen is something we've already seen before, which is the factor and cancel. So that's your whole, or your removable discontinuity. Okay? If you have a factor and cancel situation in a rational function, you will get this type of behavior every time. Right? Another thing that happens is like what we saw in these previous two examples. It depends on the multiplicity of the root of the denominator that you're looking at. Okay, what is multiplicity? When you've got a polynomial, that polynomial is going to factor where you're going to have an x minus k type thing for each of its roots. Okay, so if 2 is a factor, you're going to see an x minus 2. When that polynomial is fully factored, the exponent on that factor is called the multiplicity. Okay, now when the multiplicity of a root of the denominator is odd, there's going to be a disagreement. We're going to have either that situation or that situation. That's what we saw in the first example. When the multiplicity is even, they will agree, meaning we'll have them both shooting off to positive infinity or both shooting off to negative infinity. Right, so rational functions are pretty predictable in this way. I'm going to put a definition to this idea of limits that go to infinity. Let's suppose f of x is something that increases without bound as x approaches c from both sides. Okay, when that happens, when x going to c makes you increase without bound, we're going to say that the limit as x goes to c of f of x is positive infinity. Okay, same thing for decreasing without bound. If it decreases without bound, we're going to say the limit as x goes to c of f of x is negative infinity. If they don't agree, okay, if going from one side versus the other, maybe one goes to a finite number and the other one goes to an asymptote, right? Like we could have two different behaviors. We're just going to say it doesn't exist. That's all we can say. Now, you might think, but hang on, when we talked about continuity, we talked about a limit needing to exist in order for it to be continuous. So, would it follow then that if the limit goes to infinity, then the limit exists and therefore it's continuous? No. You see, infinity is a concept. So, when a limit goes to a plus or minus infinity, it still technically doesn't exist, right? Even when this is true, the limit does not exist. This is just a particular and special way of talking about a type of limit that doesn't exist. It's describing a certain does not exist behavior. Okay? So if the limit goes to infinity, it does not exist. It's just that by saying it goes to infinity, you're describing a particular behavior, a particular way for it to diverge is a term that you could use. Here's some properties that we're going to get regarding limits that go to plus or minus infinity. If we know that f of x goes to infinity and g of x goes to some finite limit L, if I add those two things together, I know that that limit is still going to go to infinity, right? You ever argue with your siblings like, times infinity, well, times infinity plus 1, well, infinity plus 1 is still infinity, and it still goes to infinity, so infinity wins. Write that, infinity wins when it comes to adding functions together. But other operations can get kind of complicated. Multiplying them together, that is not so predictable. That limit could be anything. It depends on how quickly g of x, how quickly and how strongly g of x gets attracted to L, versus how quickly or how strongly f of x wants to increase to infinity. Right? We might talk about something like that if we study L'Hopital's rule in a Calc 1 or in a Calc 2. What if I divide? If I divide, that could still go either way. Could also be anything. Again, it depends on how strongly f wants to increase and how strongly g of x is attracted to that L. So you can get lots of weird behaviors when you take limits and multiply them and divide them, right? And these are things that, like, we didn't have all this uncertainty when we were talking about two functions that both go to some finite number, right? This is an extension of I called it the things we expect theorem. I wish I could show you a card, but I don't have one prepared. The things we expect theorem had a k here, or maybe it was L and k, doesn't matter. And it made all three of these work just the way that you thought they would, right? This would go to the product of the limits, and so the sum of the limits is the limit of the sums, the product of the limit is the limit of the sums. That works only for finite limits. It does not work if something is blowing up and going to infinity. Okay, so that's another reason why it's dangerous to think about a limit to infinity existing. It doesn't exist because it doesn't obey the properties that it should for other types of limits that do exist. However, these are some things that will always work. If you have a function that goes to infinity, taking 1 over that function will go to 0. Absolutely. Okay? And in fact, it's going to go to 0 from above. It's going to decrease to 0. If a function is going to 0, 1 over that function is going to shoot off without bound. And that could be from the left or from the right. It depends on how exactly f gets to 0. Does it get there by way of negative numbers or positive numbers, or maybe it's oscillating, right? Whatever happens, there's going to be some kind of increase or decrease without bound here. If a function goes to infinity, then the negative version of that function will go to negative infinity. Right? That should seem intuitive. And then what if we multiply by a number? If we take a positive number, and suppose we have a function going to infinity, then that constant multiple of that function will go to infinity as well. Okay? Now, why the specification that a is positive here? It's because if a was negative, we would have to combine it with this fact and say, okay, if a is negative, it's going to then go to negative infinity per this. Okay? So with these two facts combined together, we should be able to say something about what would happen if a happened to be negative. Yeah? Let's try a couple of examples. Let's consider the function x plus 1 over x. As x approaches 0 from the right, x approaches 0 from the right, that's kind of tautological. That term's going to go to 0. This term is going to go to 1 over 0 plus. I'm going to introduce the idea of this infinitesimal. The infinitesimals, we call them 0 plus and 0 minus. This means you're approaching 0 by way of positive numbers, or approaching 0 by way of negative numbers. Okay? And 1 over 0 plus, when you're saying, I'm going to 0 from the right, that's going to go to infinity. Okay, now these two, I'm saying these two things are equal to each other. However, neither of them actually exist. These are ideas, these are concepts, these are ways to describe certain behaviors that happen with this function. Okay, it's a tool that helps us describe the behavior of what this function is doing near 0. Okay, so the x plainly goes to 0 by direct substitution, and then the 1 over x goes to positive infinity, and 0 minus infinity is going to be negative infinity. Okay, and there's your answer. Let's make it a little bit more interesting. Let's find and describe all of the vertical asymptotes of cosecant of x. Now remember, cosecant, I want to leave myself a little more room there. Cosecant of anything is equal to 1 over the sine of that number. Okay, so as we're thinking about cosecant, we're also going to keep the idea of sine in our minds. And this matters because when sine is 0, we've got some funny business happening. When sine is 0, cosecant has divide by 0 type funny business. Okay, so when does sine return 0? Sine is going to return 0 at the points on the unit circle that have 0 for a y value. That is right here and right here. So x, we're going to think of x as the angle. Okay, so what angles make the sine return 0? Well, this one is 0, and then when I go over here, this one's pi. But wait, there's more. From pi, I can go down and around this way and arrive at 2 pi. Okay, and then I can do another pi, another half circle, which is going to give me 3 pi, and then keep on going. Here's another one. Here's 4 pi. I do another half circle and I get to 5 pi. Okay, so there are infinitely many ways. There are infinitely many x's that will make sine return 0. There are infinitely many x values for which sine of x will return 0. And they are all integer multiples of pi. So n pi, where n is any integer. Now, the behavior at all of those possibilities is actually going to be dependent on whether sine is even or odd. Or, sorry, not sine. Whether n is even or odd. Let's suppose n is even. Okay, and then let's let c be n times pi. So c could be, we don't know what it is, it's arbitrary. C could be 0, it could be 2 pi, it could be 4 pi, it could be 6 pi, it could be negative 2 pi, it could be negative 4 pi. Okay, we're going to try to say something about the behavior of all of those things at the same time by letting n be arbitrary. Okay, letting this n be arbitrary instead of choosing one will establish the behavior for all of them at once. Okay, now if c is equal to n pi and n is even, then we want to think about angles approaching this way and this way. Okay, so let's consider limit as x approaches c of cosecant of x. And we want to consider the left and the right separately. All right, now when we approach c from the left, we're not talking about the left side of this graph. We are talking about smaller angles. X is an angle on the unit circle. Approaching c from the left means you are turning around the unit circle by way of a smaller angle. Okay, so c is this angle right here. A smaller angle is going to approach from this direction. Okay, x approaching c from the left looks like exactly what my cursor is doing here. Ooh, maybe I'll make that bigger so you can see. Okay, here is x, the angle x, approaching c from the left because c is right there. All right, why does that matter? Because down here, sine is negative. Okay, so as x approaches c from the left, sine is negative. Therefore, 1 over sine is also negative. So it wants to go to 1 over 0 by way of a negative number. So this is going to go to minus infinity. All right, same thing in the other direction. We are approaching c from a larger angle. A larger angle is going to come in this way. Okay, x approaching c from the right actually looks like this, right? Because picture it, this angle right here is larger than that angle right there. This is more of the pie. You know, if you picture that pie slice versus this pie slice, that one's bigger, right? So larger angles are going to come down from above on the unit circle there. Okay, up here, your y values are positive, so sine is returning all positive numbers. So that's going to go to 0 from the right. Sine goes to 0 from the right. So cosecant blows up to positive infinity. Cool? So the behavior at an even multiple of pi will go like this. From the left, it goes to negative infinity, and from the right, it goes to positive infinity. Now let's consider what if n is odd. N is odd, and c is still equal to n pi. All right? We're interested in limit as x goes to c from the left of cosecant, and limit as x goes to c from the right of cosecant. Okay, and when n is odd, we're talking about an odd number of pi's. 1 pi is half of a circle. Right, so 1 pi lives here. From the left, we're talking about coming in from a smaller angle. What angles are smaller than pi? Well, this one is. Okay, so as we're approaching c from the left, we're going to come down on that point from this direction. Okay? And what is sine doing up here? Up here, your y values are all positive. So up here, sine is positive. Which means sine is going to go to 0 from the right. Therefore, cosecant will go to positive infinity. Okay? What about if x goes to c from the right? X going to c from the right means you're approaching from bigger angles. What kind of angle is bigger than pi? Here's one. This angle is bigger than pi. So we're going to approach from that direction. Down here, sine is negative. Okay, so as x goes to this point from the right, sine is negative. Sine is going to 0 from the left. Okay, this is 1 over 0 minus, because 1 over cosecant is negative there. So that goes to negative infinity. So in summary, let me draw those for you so you don't have to watch me. Boom, video recording magic. Okay, so when your n is even, when the coefficient on your pi is even, we have this type of behavior. We have going down from the left and up to the right. So that's for all of the even multiples of pi. When n is odd, I didn't sketch this one. From the left, it's positive infinity. From the right, it's negative infinity. So it does the opposite. So you have that and that. You have that and that. Going up and going down. Now this is kind of cool. Look what happened here. If I were to just connect that little spot in between all of those, doesn't that look like the graph of cosecant that you know and love? Because I know you guys all know and love the graph of cosecant. Who wouldn't? In case you're an unfortunate soul who doesn't, I'll show it to you. Here is cosecant, and then I've also got some choice asymptotes there. Alright, we sometimes think of cosecant as making almost a parabola shape. It's really not a parabola because parabolas don't have asymptotes, but you could say it's a U shape, or it reminds you of a parabola, and I wouldn't bite your head off. Okay, so we can see here is pi. So as x is approaching pi, this behavior is showing up here and here. As x approaches 2 pi, this behavior is showing up here and here. Okay? This is why the graph of secant and cosecant do what they do. Because of the spots where sine and cosine equal 0 or 1, where they either match up or blow up. Right, so this is a description of all possible of the infinitely many asymptotes of cosecant. If I just picked pi because it's nice, that would have described a particular asymptote, which you could do correctly, but it doesn't, as the question asked, describe all of them, right? It wants all of them. I don't know, man. I just love the concept of infinity. I could talk about it forever. So there we have it. Now you know something about limits that go off to infinity. Keep practicing and have a wonderful day.